Alright everyone, thanks for coming to my Masters in Robotics Speaking Qualifier. I'm with Nish and I'm going to be talking about bi-directional reconstruction and avoidance today. And I think you all know, but the way this works is I talk about for 45 minutes, and the thesis does the Q&A. You guys are free to ask clarification questions, and then after the thesis committee is done, it's your chance to ask stuff. Alright, so without further ado, let's begin. So I'm going to motivate this problem by sharing that wires and power lines are one of the hardest obstacles to date for a UAV. So on the top right, you can see that by the time you actually see them, it's generally too late. And it's also very hard to see them in general because they can be similarly, they can look similarly to things in the background, edges, straight lines, and curves. And the second thing is, it's hard to see them across multiple sensor modalities. So here we have an example from a real flight list at Kaess, a site half an hour away from CMU. You can see the RGB image from a drone's point of view, and it's the disparate image, which misses the thin obstacle. And here we can see the output of our method, a CNN, which is able to see it in the camera, which we can eventually use it for avoidance and inspection tasks. And here, even though like LiDAR can still see these power lines, you need a really dense point cloud, and probably you need a really heavy payload on your system, and you just need to spend a lot of money to buy that expensive LiDAR to map things for you. So basically we want to do everything with the monocular camera under a known state estimate. And there are also a lot of crashes each year just because even humans have a tough time seeing these things. And then there are a couple of niche industries in which this is really useful and can make you a lot of money, which is like if you can come up with a device which can detect and avoid wires, you can put that on a helicopter. And also there's this industry called power inspection, in which you have to send someone on a helicopter alignment to find spots where things aren't working well, and then sit down there and work. And then there's, and you need to obviously spend a lot of money on that. And this kind of motivates one of the parts in our talk in which sometimes you need to reconstruct the curve exactly. And to do that, if you miss some detections, if there was like some structure you could exploit in this problem so that you could clear that tree away from the wires. So if you're not convinced, here you can test yourself. By the time you see wires, it's kind of too late. And these are all public videos of people flying drones or parasailing in this case. And so there are other applications as well. And then people doing dangerous tasks and risking their life. And this is a funny example if you're flying a 3D solo. Sometimes this can happen, and again, you might need to use a water jet, which might or might not work. And similarly, if you're trying to be cool and flying in front of your friends on a weekend, where you might end up just making a fool out of yourself. So again, like this is the last example. You thought you were very close, but you just crashed. So with that, if you rate my abstract, this is a thesis of 3 parts. The first part is we want to find things in the monocular image. So the input is here like an RGB image, and there's some black box, and we want a per pixel wire segmentation out of this black box. So that's the first third of the talk. The second third of the talk is once you have these segmentations, can you localize these wires? So we propose 2 methods. The first is the obvious thing you do. You'll be like, I'm going to binarize the output, the confidence value from a CNN, and I'm going to use some sort of a voxel grid-based mapping method. And this is an efficient way of doing that, just using images. So we'll talk about this in detail. And here you can see this is sort of like an inspection task in which you are seeing missed detections, and you can reconstruct them with those blue and purple kind of voxels. And the things in the background are actually just observed by the stereo camera. In the second, another thing that we propose is that if you know where the wire is, where you are, can you exploit this model and minimize some sort of reprojection error to reconstruct the curve exactly? So here you can see like a toy example of known camera poses. You're flying towards the wire, maybe flying up and down. You initialize here, and the black is the ground truth, and you're kind of minimizing actually the reprojection error. And the last part of the talk, we close the loop with our model-free voxel mapping method with a simple reactive trajectory planner library. And this is a test run we did in National Robotics Week this April in the open area between NSH and CIC. And the mission is very simple. You fly towards a wire, there's a goal point, you fly up, and then back down, avoiding it successfully. So with that said, let's zoom into the first part. So here, the premise is that we are trusting the deep learning people or the computer vision people that well, they can do really great things with semantic segmentation. And it's generally a black box which people come up with in some heuristic fashion. So we want to figure out what this black box is. But even before you figure out what that black box is, you need some amount of labeled data set. And for our problem specifically, there is none. Or there is a small one which is not that useful. So this is the first question. And the second one is, how do you design this black box? And you want to make a good black box. By good, I mean it should be able to run on a TX2 at a decent speed, say 3 to 4 hertz. And then also, it should have a good accuracy. So, and we are not the first people to do this. So back in the day, starting from 2002 itself, like people have come up with various hand-coded methods, which are essentially engineering. They say that given some image, we'll find some edge map, and then we are going to probably use something like a Huff transform. And the underlying assumption is that these things are straight line in number. Then another paper, they assume that, well, for inspection tasks, we know that they are just 3 or 4 in number, and they are all parallel to each other, so we can cluster in the space of orientations. We can assume there's some specific intensity distribution, so we can come up with a hard-coded kernel. Like we can say that these are probably Gaussian distributions. And some of the people even go as far as just assuming that there would be no occlusion, so it's going to be throughout the image. So the gist of all this is, like, some of these papers do work well on their specific application scenario, their small data set that they release or didn't release. But at the end of the day, they demand a lot of parameter tuning. And so to bypass that, so we are saying that let's design a differentiable black box, which can be pre-trained on some amount of data set, like some sort of an ImageNet kind of data set, and then handpick some images from our test site and fine-tune on that. So the question that we were trying to ask, the first question was how to deal with a lack of labeled data set. So we just like render synthetic wires in a ray tracing engine in their specific shape and also the straight lines, and we scrape a lot of publicly available FPV flight videos from the internet. So to give you some numbers, this is a synthetic data set of 154 flight videos comprising of 67,000 frames. You can see this is not clean. Like some of these things have logos, a couple of selfies here and there, but this gives us like some sort of an image net. And we vary the orientation, the number of wires, the texture, and all that. So, but how can we come to designing our own black box? So at the time of research, and someone might even say that this is so 2015 in terms of deep learning literature, but at the time of research, these two were like the state-of-the-art papers, and they are essentially built on this, the same high-level idea that somehow gathers some sort of global context in my image, some global signal of the object I'm trying to detect. So for example, in this image, these people are trying to detect a dog. So they downsample the image, have some differentiable parameters, and get some signal of there's a dog in the image in the middle. And then they come up with this upsampling module in which they try to localize where this dog might be. Similarly, fully convolutional networks, another state of the paper at the time of our work, kind of downsamples, get some global aggregate in the red part, and the blue part tries to figure out where these things might be. But then if you think about our problem, this is exactly unintuitive, because if you have a thin obstacle, why would you downsample in the first place? So how can we deal with that? And also, how can we gather context? So because we don't want to downsample, how do we gather context without downsampling? So to deal with that, then we take this idea from this paper called Dilated Convolutions, published in ICLR 2016. And basically, the idea is very simple. It says, let's make kernels sparse. So I'll walk you through this image, this 1D example. It's bottom to top. So the blue thing is like the input signal here, and we are doing convolution on this 1D signal with a 2 pixel wide kernel. So here you can see at hidden layer 1, each feature is influenced by 2 pixels in the input image. And then in hidden layer 2, if you try to make your kernel sparse, basically skip each thing in the input, eventually in hidden layer 2, one hidden feature is looking at 4 pixels, so it's exponential. So like 2 layers deep, you're now looking at 2 raised to power 2 features. Then you extend this idea and jump every 8. So then 3 layers deep, you're looking at 2 raised to power 3. And then finally for yellow, this thing is being informed by the whole region, this region. So this is an idea for gathering context. People applied this to 2D. There's a small GIF which is showing that how a sparse kernel works. So one pixel in the output is influenced by 5 here, even though the learnable parameters are not 25, they're just 9. So you're scaling linearly, but the things you're looking at are exponentially increasing. And similarly, you can apply the same idea. So we have some heuristic that we should be using something like this to build gather context. So this is the core idea. So what I did was, I'm saying our task is kind of not that hard. We are looking at some specific kind of edges and lines. And the state-of-the-art papers at that time around showed that you can get the some sort of lines and edge features within 2-3 layers of some network like a VGG. So we get some sort of a signal. There might be wires or similarly looking things. And then we come up with these dilated convolutions which gather context. And note that I'm not downsampling anywhere. So the input size is exactly as the output size, and also each of the feature sizes there. But I'm saying this is a heuristic. No one knows what's the right answer. If you think about it, the vision community was doing reinforcement learning together, like trying different things and figuring out the things that work based on some heuristics there. So to do this, I won't talk about the details. We did some grid search based on these heuristics. So let's go right to left. So context module, when I was showing that image of dilations, we don't know how much context we want for a wire. Maybe we need to look at the full image. Maybe a 50 by 50 field of view is enough. So I basically keep on increasing the number of sparsity in the kernels in the context modules, and I do 6 of them. And then for front end, I vary like the number of layers and the number of parameters they have, because I don't really know how many parameters we need. And the only way I can design this black box is I've got scripting skills and we have a DJX in the lab, so we're gonna run them on, right? So that's the whole idea. How do we evaluate them? Well, we use that small data set which was out there because we don't have labeled data anyway. So there was this paper in 2009 which has 42 short sequences of power lines and wires and semantic segmentation labels. We split it as the way like 2 of the other papers did in the past and compared it with them. So this basically shows like our top 15 models out of our top 30. You don't need to care about what these notations are. The whole point is these 3 columns, and these are the 3 reward functions in some sense, what we wanted. Darker the hue, the better the network. So this is average precision, which means like we want more accuracy. This is the speed of the network on a TX2, because we want to put this thing on a drone. The last thing is the number of learnable parameters. So, and this is, we handpick, like we value speed, really, maybe we are trading speed with accuracy here, we are trading accuracy with speed here. We pick the bold ones and call them R's and compare them with baselines. And with more metrics, the state-of-the-art networks, the fully convolutional networks are 2 variants of fully convolutional networks, segment, the non-deep learning paper which includes this data set, another deep learning paper, and long story short, we beat them across various metrics in terms of accuracy across data sets, F1 scores, receiver operative characteristics, and speed. So, what this video is showing here is result on a test data set with a network trained on only synthetic data. So actually there's not a single image used to obtain this result. So this is again kind of like a drawback. You would say that you don't really, at the end of the day what really matters is your train and distribution similarity, and here it's picking up on a lot of false positives, but in some regions it does well. So what we do in practice is use our ImageNet data set and fine tune it on a small amount of real images. I think this So here's another run, and at Kaess, there's a stereo camera and a monocular camera mounted on the drone, and this is an avoidance example. But right now we're just looking at semantic segmentation of this wire, and you can see this is running at roughly around 3 Hz, and we are able to see this. So, and we'll have more examples of the semantic segmentation throughout the talk. But now we can move to the next part. Before we move, these are the messages that you can take home with you, which is do not sample, do not downsample if you're trying to avoid thin obstacles. Use sparse kernels because you still need some context. You don't know how much context. Maybe do a grid search or learn how to build a network itself. Generate some synthetic data, but don't rely on it completely because still training and testing distributions matter. Hand label some images, and things would work. And the last point, I didn't really talk about it till now, but this is basically saying for this problem, false positives are bad, right? If you see another road lane, maybe it's bad. But false negatives, if there was a wire and you didn't really register it, it's kind of worse. So maybe you can resolve false positives somehow with a higher recall network. How can you do that? Just to use 3D geometry, right? Which brings us to the next part of the talk, reconstructing these things. So to recap, I'm going to talk about 2 things. This one is the model-based method in a lot more detail than the model-free method. So let's just jump right into the model-free first. So the question we are trying to answer here is, this is a toy example of a drone moving up and down, and you can see the odometry here. So here are like 3 observations of these wires. From up top, looking down, you might see 3 wires like that, and then in the middle you might see this, and in the bottom you might see something like that. And the answer is kind of intuitive, like if they are straight lines, they are just intersection of planes, right? Either you can do that geometrically or do voxel grid-based mapping. But we here specifically build on work by a master student in our lab, Kaess, sitting right here. So what he does is voxel grid-based mapping, but in an efficient manner. And we combine this thing with the first part of the talk. So this is an illustration that you would generally do to map a point obstacle if you had a monocular camera. So you essentially are getting some sort of a bearing measurement. Like in classical robotics, probably you will inflate the configuration space. But here you're saying you can just do everything in images using building on the projection model of the camera, that there's some Gaussian uncertainty in that bearing, and as you go further away, you will be expanding things more and more from the camera. But what do you do? How do you translate this idea to wires? So for wires, we say we want to avoid them as soon as possible, or relatively as soon as possible. So we come up with this heuristic that we want to start moving away from the wire if we are at least 4 meters away. So we generate a fake depth image, which tells us that this wire is 4 meters in front of us. And then another fake depth image, which tells us that this wire is 20 meters away. So you can imagine this is actually a cross-section of a plane in 3D. But the whole point is we don't need to, this is just a representation of that plane. And then there is some occupancy inference going on in the back end, which allows us to reconstruct this. So in practice, this looks like, for the simulation example, this looks like this. If you are up here, you can imagine that there's some plane in which you don't know where the wire is. Similarly, when you're observing this, you are uncertain to a certain extent, like 20 meters away, and starting from 4 meters, that the wire is there, and again from the bottom edge. And then in the end, when you fuse these measurements, you can reconstruct the wire. And here's this thing running on a real test site at Kaess. So before I play this video, on the top left, here you can see the RGB image. Here you can see the stereo image, which won't see the wire. Here's the 95% thresholded output from our semantic segmentation network, which can kind of see the wire. And then this is like the dilation part I was talking about. So here we can, so the black boxes in the 3D view are representing where we think the wires are, and everything else is colored by height, and that's coming from stereo camera. So what this video is actually demonstrating is that you can map the things seen in the disparity image along with the things seen in this monocular image using voxel grid mapping, but done in an efficient manner, just using images. So now when this thing turns out, we start following the wire, and then the idea becomes very clear that we don't know, we can't really reconstruct the depth, but we can be conservative about the depth if we don't have enough viewpoints to reconstruct it. And then we eventually close this, close the loop with this method in the third part of the talk. So to wrap up model-based, to wrap up model-based, what we said was that this thing can work in conjunction with arbitrary obstacles. And another thing which will become clear in the next part of the talk is that we don't need any sort of explicit correspondence. Like if you have multiple wires, you don't need to match edges or anything. You can just use the edge map at each keyframe and do mapping. But then what the model-free method can't deal with is occluded edges and also missegmentations by the CNN. So by that I mean, like, if you observe a part of the wire, if you knew this is how wires look like, maybe you could infer that it's generally along this curve or a straight line. So our model-based method will let us do that. And for motivation for the model-based, recall the example from the first slide. There is a lot of money if you can reconstruct wires exactly and say this to a company which sends helicopters with linemen, which try to estimate visually how far it is from a wire, and then more people to cut things. So with that, we come to the model-based method. I have to fix this. Okay. So the research questions that we are trying to ask here are, we are saying we'll be given at test time some segmentations with known camera poses. We are saying there's some model, I'm not telling you what the model is right now, and there is some objective function, the reprojection error, which we have to minimize. That's the idea. The sum model looks like kind of like this. So we're just showing that this model is interchangeable, we don't know what's the right thing. We can back project this model, and at the end we have to somehow compute the distances between these two curves. So the first question is, what is the model? And we want to find like a minimal parameterization, because it's good to have the least number of parameters you can optimize for so that you can scale this up. And then we also want to understand how do you evaluate the distances between two thin objects, because in general it's very hard to define correspondences for edge-like features or line features or curve features, or even making features of such objects. So let's look at what a catenary model is. Well, whenever you suspend a rope at two ends, it's trying under uniform gravity, under a fixed mass distribution. If you solve this force by diagram, there is an implicit structure involved. We'll talk about that later, but this thing is all around you, in chains, in bar lines, and also you can imagine, like, in a soap film, if you have two rings, so it's trying to minimize its energy, and this is like the surface of the revolution there. So, but that is not the point. The point is, there's some equation, and it turns out that this thing is actually just a planar single parameter curve. So what that means is basically it's on some plane, there's some origin, and so these are the coordinate axes of this plane. By cat I mean the coordinate axes of z and x and y is 0. And all I need to define is this single parameter a, and you can see as h increases, this curve starts to become this straight line, and we want to optimize for this parameter. These parameters, basically the transform of this frame with respect to some arbitrary world frame. And the cool thing here is you don't need to model an SC3 transform because this thing is in the plane of gravity. So the only thing that you need to do is define your word frame at your takeoff point, and if your drone is sane, it's going to take off anti-parallel to gravity. So you only need to model the yaw, and you also need to model the sal. So these 5 parameters together define our model, and this is the takeaway. There's some model you want to optimize from, there's some equation which can bring this parameters to world coordinates. Now I'd look, but before we even go to optimization, we need to define what is the objective function. So here's the toy example from NSH back here. You get an algebraic image. You run the segmentation from the first part. There's a wire here, trust me. Then you have some catenary model. Now you need to find the distances between these two things, where the whole idea is take the distance transform of the segmentation and evaluate your projections at that value. So you escape any sort of correspondences, and distance transform are really fast to do. So you basically are defining some sort of residual vector for each of the n images you receive. So for each jth point, you only need to query those pinpoints in each view. And then you just take the L2 norm of this big residual vector, and that's your objective function. But we are not completely done yet, because this is nonlinear optimization, and initialization matters, and so do invalid pixels if they go out of the image view. So just to formalize this, if something is inside the image, you're just going to take the distance transform of that particular view from the segmentation and evaluate it. But what happens if something is outside the image? You can't just ignore it. Maybe you try to extrapolate it from the center, but then your objective becomes non-convex as it's discontinuous and non-differentiable at your boundaries, but you want it to be continuous and differentiable from your boundaries. So the idea is straightforward. You just extrapolate from your boundaries. And that means if you wanted to evaluate your function at that green pixel, Pij, you find some corresponding pixel at the boundary, which is given by these arrows in 8 regions outside the image, and we call this P boundary. So you get the value of the distance transform at this point, which is this. You find the distance between these 2 points, and then you normalize this distance. What do you normalize by? You normalize it by the diagonal of the image, because the diagonal of the image is the maximum possible value of the distance transform. You might be thinking this is such a detailed engineering thing you're telling me, but this is what actually makes this work and robust to any sort of arbitrary initialization. And similarly, if there's an image, there's a point here you want to evaluate, find the corresponding boundary point, and this works. So similarly for other points here, for any arrowhead, the boundary point is at the base of the arrow. That's it. So let's just summarize the objective function. And why did we do all this? We want to handle arbitrary initializations. We want to handle invalid pixels. Because if you're paying attention, I haven't talked about the width of the catenary. Obviously, there's a width, right? So what we do is figure out some heuristic of the width and the resolution. But this can handle that. And you don't need to model the endpoints. The whole point of doing this is that you only need to model the vertex. So they're just 5 parameters, and it's efficient. How do you do that? You compute the distance transform for each of the binary images once, and it's 1 milliseconds each. For invalid projections, it's Uber for distance for your objective function. You do it in a non-demand fashion by extrapolating it. So finally, we can talk about optimizing this objective. Recall nonlinear optimization. There are some model parameters. There's some distance there's some residual vector. There's a big mapping. Just to make things concrete, you're going from the model parameters to points in the word frame with that catenary equation. From points in the word frame, you're going to the points in the camera frame with the extrinsic matrix. Here, you don't need that ugly Jacobian if you are trying to differentiate this matrix, because you're assuming that your state estimate is correct, so you don't need to do any sort of algebra or anything. Differentiate, then you just have the intrinsic matrix. Again, it's differentiable. And from the subpixel coordinates, you go to the distance transform value. Again, so for a residual vector, there's the Jacobian, which is exactly what I said, in reverse order. Word frame, from category models to word frame to cam frame to pixel coordinates to distance transform. The cool thing is, you can optimize this a bit as well, because I just said this thing is constant, because to go to a cam frame, you go from the word frame, apply the rotation matrix, you differentiate this is constant, take it outside the loop, and there's some small optimizations you can do to make this thing work really fast. And we throw all this to a nonlinear optimizer called trust region differentiable path. What does that do? Here's a simulation example. I'm rendering a catenary with random camera views. 4 camera views. Here's how the model is being optimized. You can see the 3D curves are colored by the relative loss. You start from the maroon thing, go up, down, and then finally converge on the ground truth, which is the black. And this is how it looks in the image space. So here you can see more or less have the answer in 8 optimizations, but we just keep it 8 iterations, but we just leave it running. And we did more scenarios. This is again the repetition for multiple camera frames. Then you might be wondering, if you just have 2 cameras, if they're just at the right place, you can still reconstruct this with an arbitrary initialization. And then one thing someone might say is, why is our generally just straight lines? So where if you increase the SAG parameter a lot, this thing is almost a straight line. And here you can see another example with the ground truth right here with some initialization there. And then for application-specific stuff, we want to be flying to the wire with some disparity, with some up and down motion. So here's an example of things like that, with 2 curves again, and then a straight line. And here you can see that I'm actually optimizing for the catenary. Just in the middle, the SAG parameter becomes something weird, which shows its true nature in some sense. Results with real data, again, that NSH CSCIC example. There's the RGB image here, the segmented binary mask here. You can see we have a lot of missed detections, and actually our objective function also kind of helps implicitly here, because the distance transform values here along the curve are going to be lesser as compared to something here. So you can see we still have that pole towards the right answer, and there's the corresponding odometry. It's kind of like if you had been observing, it's like 8 steps back, 8 steps front almost. So this is how the results look like. Here are the 16 camera projections. You can see a lot of misrestrictions, the loss function, some arbitrary initialization, and the convergence to some results. And this kind of demonstrates empirically that the model-free method won't be able to handle the misredictions. So to end the model-based part, we can come to the takeaways. I propose a minimal parameterization of the quaternary curve. If you were to do bundle adjustment of that, you will be optimizing for hundreds of 3D points, but all you needed was 5. And if there's a structure, you better model it and exploit it, because you can do things better. For the objective, we said you never need to evaluate pixel correspondences, at least for a single curve. So you can just take the distance transform of the curve segmentation, and you can also handle invalid projections. So future work inspired by a failure case. This is again avoidance scenario with 2 examples. Here you can see that these views aren't enough, and the black is the ground truth. And even though in the image space we are doing something reasonable, because our width was kind of heuristic, and here our width estimate of the catenary curve was wrong, we are converging to the wrong answer, even though our loss is going down. So we want to fix this by figuring out how much extent of the catenary we are seeing by compensating for a roll and pitch of the camera, and then you can essentially think that there's like a viewing region, like an intersecting region of the observations you had, and we will come up with a better way of computing the width. Or else, you can also put this in your as an optimization variable, or penalize your loss functions if some of the things don't match. The second part we are working on right now is closing the loop, which means somehow computing occupancy and using it for collision checking. So that's kind of relatively simple to do, inspired by the model-free method. You go to the first camera pose instead of the word frame and do everything in inverse depth coordinates. So you change your 3 parameters instead of x, y, z. Now I'm calling some psi, and I'm saying the UVD of the vertex in the first camera position of the observation. The yaw state is with respect to the word frame, and we had, till now we were doing things with this model, but we know this is just unprojection. There's some function inverse the intrinsics and extrinsics, and this is a Jacobian. So what is the point of this? We know in inverse depth coordinates, everything can be represented with Gaussian uncertainty. So if I know the uncertainty in the inverse depth coordinates denoted by sigma psi, I can just linearize this mapping and get a first order approximation of the covariances in x, y, z, and I can put that to any sort of sampling-based planner or reactive trajectory library-based planner just by this rearrange result. And it's like, what is the sigma psi? Where do you get that? But you can get that from the solution itself. So you have to go back a bit and recall that now instead of solving for theta, we'll be solving for psi, which will be going to some residual function. And again, you can get the estimation of the covariance by the Jacobian and just invert it and then project it to theta. One thing we haven't shown at all is what to do if there are multiple wires. So one way is, if it can give me instantaneous segmentations of the curve, I can just run my algorithm in for loop in an O-N wire fashion. But if there are intersections in the curves, then the problem becomes really hard, and you have to do some sort of curve-to-curve correspondence. So if you want to extend that work. The last part of the talk, we go back to the model-free method, and then we couple this thing with a trajectory library planner. So recall that there was some way I didn't really talk about how doing boxer-based mapping with a list of inspired images. And we have this trajectory library going straight front, up and down. And then we just have a way to infer occupancy, and we do these things together. And this is again work done using work done with Kaess. So here's what it looks like. This was our demo this year for National Robotics Week. So you can see we are avoiding categories. But this is what we see. What the drone sees is something not as exciting. Also, this video first shows that the state-of-the-art drone for collision avoidance, now probably Skydio by that time of making this video with DJI Phantom, doesn't show up anything in its app if you fly it near a wire. But if you fly it near this ladder, you can see it shows that 1.5 meters away. So it can detect things which are not wires, but not yet wires. So this just shows another semantic segmentation result first on just demonstrating that we can find wires and images using some confidence map. And then we finally come to another avoidance scenario. Again, RGB on top left, disparity, semantic segmentation output, the bloated semantic segmentation output in terms of like just Gaussian uncertainty in the image space. And this is the thing we were talking about in model-free mapping, that it's essentially just a plane, but it's a truncated plane. And if you have a camera view, so you can imagine it's like a section of a system. And here we are just being conservative, that we know we are seeing this wire, we are flying towards it, we can't really reconstruct it, but we have this trajectory library planner, and right now it just told us there's something in front of you, fly up, and the robot flies over the wire. And then there's another run, we did 10 runs of this, and here you can see that there's actually a lot of motion blur in the RGB images, but our network can still reconstruct it. And this is just a repetition of the results I showed earlier. So now we are moving towards the end of this talk, and we did 3 things. So let's just do a brief recap. The first part was segmentation, also known as how to train your black box, and somehow we did too. So the takeaway from that part was don't do dot sampling and use dilated convolutions to gather context. Generate some synthetic data, use our data set, label some real images to fine tune. You need some small amount of real data. Use a higher recall network so that, because of the fact that false positives are not as bad as false negatives. Then reconstruction, if you saw some wire in a monocular image where the wire actually is. The first part was model-free. We are doing some sort of auxiliary-based mapping. And the cool thing about this is you can just couple this with a stereo camera and then reconstruct wires and not obstacles. And again, you don't need any sort of correspondences. You don't need to think about this. But like a slight drawback there is that you are not exploiting the implicit structure in the problem. So if you're just relying on your semantic segmentation network to see everything, if you miss something in between, you'll never know what to do. Enter catenary curves and optimization. We propose the minimal parameterization of the catenary curve. We are just saying there are 5 parameters. We introduce a loss function which can handle arbitrary initializations, doesn't need any sort of correspondences, and can also handle invalid projections going out of the niche. Avoidance, you want to fly away from the wires, not fight them because they're dangerous. So we demonstrated the model-free method, the voxel grid-based method coupled with a trajectory library planner. So how you can extend this work if you have a thing for catenary curves? The first part is segmentation. Like we talked about so much about model-based curves. In 3D, there also could be, you could also model things in 2D itself, because at the end of the day, at max, this is like a second or third order polynomial if you look at the projection of the catenary. Like these days, people are doing multi-view stereo, in which you just have some loss function in 3D, and you then learn, because all these matrices were differentiable, you would have some global loss function, maybe in 3D, or just even in 2D, and try to impose that things need, like wires are continuous in some sense. Is that what I say? Published a paper called EPUB transform. We actually tried this. Daniel tried a bit more than I did, or like maybe Daniel, keep catenary detector. And then maybe you can also learn to build your own black box, because network design is a reinforcement learning problem. Maybe you can do better than the 30 networks I trained for a week on the DGX. But this is like a simplification. Everyone can say anything is an RL problem, so in practice, this is still hard, and you need to design some reward function. But that's a way to do this. For reconstruction, I'm just going to talk about how you can fix the model-based method. I guess I already talked about it, but to recap, we want to close the loop by modeling the uncertainty with the inverse parameterization. We want to reconstruct multiple wires, but for that we need some sort of curve-to-curve correspondences in the images we are seeing. And if you remember that false positive in which we converge to the wrong yaw value, either we can compute the width of the catenary just because we know the camera calibration matrices and we know where the extent of the intersecting regions from our odometry. Either we can just come up with a maximum fixed width and that would work, or else we can put that as part of our optimization problem in terms of parameters or just changing our objective function. For avoidance, we have demonstrated short-range avoidance, but in practice, if you're a helicopter flying at a few reasonable knots, like kilometers per hour, you'll want to avoid things far before they are like 4 meters or even 20 meters away. So maybe you can couple this thing with a sampling-based planner. And this is 2 years of work in GIFs. Somehow, for reasons we don't know why, segmentation paper was nominated as a finalist for the Best Application Paper Award in IROS last year. Worked done with Daniel and Basi's everywhere. And Gitesh's work was accepted this year in IROS, the model-free mapping and the avoidance, and closing the loop, everything. I'm still working on this with Kaess and Basti and trying to submit to ICRA. If you read my abstract, the last part of the deliberate avoidance, we did something with Sam and Brian, and we submitted to Curl. And here you can see just like a toy example that somehow we are able to change the sampling distributions as the tree is changing for 2D problems and the scanning problems for the people in the back. This thing, there's a kernel density estimate showing the distribution in these 2D problems, and these green things are again samples from a distribution. And this work hadn't been possible given for all these people up here. The first row is actually like the row of my extended advisors, apart from Basti, the PhD students in our lab, Dan and Gitesh, Sankalp, not Gitesh, but almost a PhD student, I guess. And Michael, who jumped in at the last minute as for the model-based method during the more or less the complete of the last semester of my master's, and John, Silvio, and Greg for building a lot of these robots and helping out in experimentations, and then Sam, Brian, and Rogerio for starting the roots of that, learning to sample people, and Rogerio again for this presentation. And Nora, Rachel, and Sanai for bringing me back to CMU multiple times. Thanks, and if you have any questions, I guess we'll begin with the committee.
It was given you had a model-free method working for robotics. It was very interesting that the first model-based method or approach that you used was actually in image space and not in 3D, given you already had some 3D estimate of how the wire will look like using the model-free method.
In practice, like, we never really brought those works together. So I mean, you can say, like, ideally we had work done which would give us an estimate. We didn't use it to be straightforward because of constraints of time. And well, so the other point you were trying to make was that the model-based method, like the future work of the model-based method is image coordinates. Then why did you start with the word coordinates as well?
Oh, no.
Or just like use the output of the model-free method, I
guess I want to ask you that what do you think would be the pros and cons of actually just doing a model fitting on the estimate of the model-free method? You just fit a catenary on it on 3D.
Oh yeah, yeah, you can come up. So people actually do catenary because there are two methods which did LiDAR point cloud based catenary fitting. Again, it's a non-linear least squares problem. Their models are almost the same as us. So people do that. But I think one issue with the model-free method in general is if you're seeing things, if you have a lot of false positives, I get actually like both methods suffer in that. Like the model-based method, the model-free method will just give you like a really fuzzy output. Like all these things are occupied, and if you use that bound as the optimization bound for your model-based method, or like say like this is the catenary envelope, like all space of the catenaries that could be, probably it wouldn't give you much instead of just like optimizing our thing in a bigger state space, just because our loss function is convex, so I can literally initialize it anywhere I want. Yeah, but technically you should be using some initial depth estimate if you have. But at the same time, a model-based method doesn't need it. Right. It still work with it. Because even in the first frame, I know the vertex or like my model, my catenary vertex is around this bearing measurement in the first frame itself. So if I just run the optimization for the first keyframe, and then I just have a big covariance in the length, which is similar to what model-free would start.
So for the geometric wire reconstruction, we assume that you have cameras perfectly localized.
Yeah.
And I guess from state estimation that it's reasonable to have at least a good initialization, but does that impact the result? And could you also maybe include the localization of the cameras into the optimization?
Yeah, so like one way to think about this is, like actually, this brings us to the inspiration of the distance transform function. It's actually an edge-based visual odometry paper by Xiaoji Shen in ICRA 2016, in which they get edge maps of consecutive keyframes, and then they're optimizing instead of catenary curves, they state estimate, gain 6 parameters like a SE3 transform. And the whole problem they're trying to solve is the same. Get a higher recall edge detector, use their distance transform, to not find avoid the problem of correspondences. So yes, you can use the catenary as well to improve your state estimate, given if it was good enough, because the catenary, as we saw, like if you don't have enough keyframes, there are degeneracies in terms of yaw, and like if you move it like this, so the sag might change as well. So there's like coupled covariances coming on there. So I think it's a way to improve your state estimate, but there are better ways to improve your state estimate by using the complete edge map instead of relying on some bias slam, like coming up with a bias slam. But yeah, you can go back and forth, get OVO, do mapping, get VO, do mapping. But I don't think it will give you much. I would rather use a better state estimate or do something on that side instead of trying to use catenaries as landmarks in some sense.
Okay.
I guess my answer is still, the reason for my answer is just because of the application. Like this is all application driven research. So like the real application is mapping things, and probably it's going to be good work, but probably not that useful.
Yeah, that's a good point. So in real applications, so you would typically see more than one wire.
Yeah.
How will you
Probably
deal
do
with
that.
that?
Let me open up the
Second
100 slides of the second book. So this is a sick graph paper this year. I really like this paper. So like the problem they're trying to solve is, and this is an alliteration going on. The problem they're trying to solve is if you're trying to reconstruct curves, and again that's a reference view or a reference curve, and then you have multiple things going on in the second view. But you have to solve the correspondence problem, right? So let's start from this endpoint. And then what they do is, well, we don't know where this curve is, so we're going to find it along the epipolar line. There could be multiple curves. So it's a combinatorial problem at the end. And they just, they sweep the epipolar lines for this segment, and that's like the yellow region. So for the center point, it's this center line. And then along this region, they say there are two possible matches for this curve segment. And before this, they are also running an instant like intersection detection thing in their image, so they know this is curve 1, curve 2, curve 3, curve 4. So again, for this segment, there are 3 possible matches. And then they just say like, we're going to reconstruct them all. And then we have some global loss function. And this is, you can see like this is a 3D object. Then they have some global loss function. And then they say there's some criteria that this thing is made from a single piece of wire. This is like wire art. And they were trying to reconstruct such objects. So, but for multiple wires, you probably don't need to solve this problem because you are moving in a smooth fashion, right? So you can reuse just your previous estimate. So this is more for a multi-view stereo, multiple wire algorithm, just random views. Then you need to solve this problem. If you have multiple wires, then you can take inspiration for something like LSD slam, like the previous depth estimate, reproject that into the current depth estimate, and do some sort of curve-to-curve correspondence. And if there are a lot of curves intersecting there, I guess then you can have like a similar 3D. So our version of this thing would be catenary curves are longer, and we maybe have some idea of the maximum number of curves which we saw in the image over this region. So we have to come up with something like this. Like this was an insanely involved traveling salesman's problem which they were solving, and making sure things are continuous at each endpoint so you can see. So this thing takes like 10 minutes to solve, if we have to avoid things as well. So that's where the why the model-free method is so good for avoidance. But this is for, the model-based method is someone who wants to chop trees off near wires, or wants to do paralleling segmentation, or like sag estimation, because they want to estimate if we need to reinforce the poles supporting the wire and whatnot.
Okay, great.
Yeah.
So for the this nonlinear optimization, there are ranges on the parameters and maximum or the unlimited.
They are maxed and min.
And so how sensitive or like what are the ranges?
So, like, the ranges are kind of a bit arbitrary as of now. So, I have some sequence. I come up with. I think I can show this in one of the simulation examples. Like I come up with a 100-meter long region in some sense. So these coordinate values, they are actually metric. So here you can maybe the avoidance example. Here it's hard to tell, but you can see that I'm reconstructing the wire 50 meters away roughly, and then I optimize this thing in a 200 by 200 kind of keyboard. But this is very hard coded as of now.
What about the sag?
The sag kind of goes from like, so when it's 0, it's division by 0. So I start with something like 1 and make it go there something like 1000. At that point, it's just like a straight line.
Okay.
There is no way of coming up with the bounds, which is like to solve that problem. What you can do is again viewing frustums, right? So if I have a camera pose here, I have a camera pose here, I can geometrically say like this is the maximum extent of the catenary, and this is how far I'm seeing, and then come up with some sort of a catenary envelope, because like your influence is sag and everything is. So you need to figure that part out, which I have.
Okay. And then the other question is, once you have the fit, what's the how do you get an uncertainty on your estimate?
Oh, like from the solution you mean?
Yes.
So the first point was, from the solution itself is basically nonlinear optimization. So there will be a Jacobian from parameters going to the residual function, which is essentially what I defined in this part, right? This Jacobian. So you just take J transpose J and take the inverse, and that's your covariance on the solution. And then what we are saying in the future work section was, initially this covariance was in XYZ, but the error is not necessarily Gaussian in XYZ, but it is Gaussian in inverse depth, just because it's projection matrix, you have this, it's kind of modeling this solid angle and inverse depth. A Gaussian in inverse depth is mapping to some long tail distribution in actual depth, because there's an inverse like there's a hyperbolic relationship between the two. So we just say that these errors are Gaussians. We somehow find the covariances in this, linearize this mapping, and just, this is a standard result. If you have a Gaussian covariance in X, the covariance, and there's a map in some variable X, and there's a mapping Y is equal to X plus B, then the covariance is A sigma A transpose, where sigma was the covariance in X. This is just that. And then probably, I'm not sure which part you were asking, this part or that part, I'm just telling everything. So you get this part from the solution GPP. Yeah.
Any other questions?
I have two questions actually. One is, you said that you should use a high recall network. Is that something do you have a network structure that gives you high recall, or is you model the loss function to give you that?
Oh, that's more of an evaluation metric. What I mean by that is, probably it's somewhere. It's just like the precision recall curve, and then you just you just essentially threshold in a way, because like this is a binary segmentation problem, right? It's outputting a confidence value. So you have some validation data set. You can compute some metric over the whole data set. It could be like per image basis, this is the output, like if if I do it throughout the data set, this is the output, and you just build a precision recall curve, which is like, because at the end of the day, you need to binarize your segmentations to do anything in the second part of the framework, right?
Yeah.
So as you will be changing recall, precision will be going down, which means you'll be seeing more and more of wires, but also more and more of non-wires. So like this is, actually I should have mentioned that in future work, generally for thin obstacles, you do want high recall, right? Even if you're doing edge-based mapping, you want to get, if you're reconstructing, say, a tree or something, even if you reconstruct a thin obstacle which was part of a cuboid in some sense, it's fine, because geometry can resolve that. So I'm saying if, instead of a catenary, you detect some boundary of some object, right, say a person or some tree, some false positive on the ground, it's fine. But make sure you get as much information as you can from the catenary. And again, the underlying assumption is there is some information about the wire in the RGB image itself, or else then you can't do anything.
Okay.
That's what I mean by high recall. False negatives are bad. If there was a wire and you didn't see it, it's really bad.
Okay, that makes sense. And the other quick question is, you seem to be using, for the loss function, use a, I guess, a linear distance function, right, from the wire. Have you thought of using something like quadratic or some other?
So we did like a Huber loss as well in the.
Does that create
So
faster convergence?
Makes for faster convergence. Yeah, I was thinking about that. Does it help or it does not help? I mean, obviously it will help because, like, if you have a good initialization, you will converge probably 4 or 5 less number of iterations than I'm doing. So it should help. But then you'll have to make sure that the Huber part, like the quadratic part, it's basically like some quadratic here and then some linear loss function after some threshold, right? So that the whole extension of the loss function I was proposing outside the image, that either you have to change that as well, or keep that linear, or just have a Huber somewhere near the wire itself. Yeah, it should help, like, because generally Huber helps in faster convergence. But if you think about the theory, actually, like, this is non-linear least squares, so it's already doing something like that. Like the L2 norm of this residual vector, it's technically approximating this parabolic thing in this high-dimensional straight space, just because the loss function is technically the L2 norm. So it's already quadratic in this fashion.
Okay.
Any other questions?
Thanks.